everyone. My name is Alice. I am education lead at ZKM, and I'll be showing you how you can use ZKM's proving service to generate proofs for your own programs. So with the proving service, any developer can efficiently generate proofs. It's an alternative to local proof generation. So if you don't have the minimum hardware requirements, which in our case is around 32 gigabytes of RAM, or if you just want faster proof generation. So if we look at this overall broad process for zkMIPS, improving and verifying the correct execution of a program, we can divide this process in three main parts. So first, we have executing that program. In our case, we compile that program to MIPS, like what Lucas mentioned in his previous presentation. And then from there, we generate a proof that proves the correct execution of that program before we do on-chain verification of that proof. So in this kind of three-part process, the proof generation aspect is covered by our proving service. And for zkMIPS specifically, right now we support Golang and Rust programs that you can prove the execution of. You can directly request your proofs to be generated through the service, and in doing so, scaling your proof generation, reducing your overall proving time, and just overall not having to worry about the proof generation aspect, and instead being able to focus on building your own applications. So just an overview of the composition of the proofs that are generated by the service. We first start off with a program. That program is compiled to MIPS in the format of an ELF binary, and that ELF binary is split into segments. From there, we generate a Stark proof for each segment, and because we're using multiple different trace tables, we may have multiple Starks for each instruction. So what we do is we combine those Starks together into a single root proof for each segment, and that root proof is the proof of the root circuit for all of those Starks. From there, we start aggregating those root proofs. So the aggregate proof is the proof of the aggregation circuit over two root proofs. And then from there, we'll continue that aggregation process until we have a single proof for all those aggregate proofs. And then as a last step, using Grout 16 to reduce the final proof size and to also enable it for on-chain verification. And in terms of the components of the proving service to help with the proof composition that we just saw in the previous slide, as our first step, the user, you would request for that proof generation from the service. From there, the address that you use has to be on our whitelist in order for you to access the service, in order for you to for your request to be granted. From there, we enter into the stage service, and that's responsible for handling all the different components of the prover. So we have the split prover that's responsible for splitting the ELF into the segments, the root provers, which generate those root proofs in parallel, the aggregate prover, which aggregates those root proofs together, and then the snark prover, which generates that final snark proof. So how this would look like on your end if you're using our service. For specifically a Golang program that you want to prove the execution of. First, you would compile that Golang program to MIPS. That's what the first statement is doing, and that produces the ELF binary. And then from there, you can directly request for your proof generation. So specifying parameters like the private key that corresponds to the address that you have whitelisted, the segment size, the path of your ELF file, the endpoint of the proving service, arguments, so that includes the public and private inputs to your program. And if that proof generation is successful, you'll generate this URL as a result. If you open it, it'll reveal all the contents of the proof. So what we have over here is, going back, what we have over here is just an example of a proof output, which is the proof with the public inputs. So going into our demo portion, what we're going to do is we're going to use a toy example Go program called isEven. So this one right over here. And as you can see, it's a very basic program that checks if an input is an even number. If not, that program will fail. From there, we'll use the proving service to generate a proof for that program's correct execution, and then from there deploy our proof on a verifier contract. And as a last step, use the valid proof to perform some on-chain action. So in this case, we are minting an ERC20. So I will go do the live demo right now, and I have to go back here because that's where my computer is. But if you want to replicate this on your side, what you should do as a first step, okay, hopefully you guys can see this. I know it's a little small. So what you should do first is clone the ZKM prover repo. Thank you, Jerome. And from here, remember our first step is to, before we go into that, this is the isEven program that we just saw on the previous slide that we'll be generating a proof for. And remember, our first step is to compile our program to MIPS. So that's what we're doing here. Oh, I need to establish a go path first. And as you can see, we have the isEven ELF binary that's generated. And then as our next step, we're going to directly request for that proof generation. And so as you can see, I specified the parameters like the segment size, the path of the isEven ELF, and for our arguments, we're not including any private inputs. The only public input we have is the number 6. If we're using an odd number, then that program would be invalid. This does take some time, so I'm going to go back to these slides very briefly. If you want to replicate this on your end, be sure to clone the following repositories that we have over here. So we have the prover, the verifier, the use cases, which includes the ERC20 mint case. And if you want to have a step-by-step guide as to completing the proving, so both for local proof generation and also for using the proving service, then we have also some guides listed over here. And right below that are just the requirements that you need for Rust and Golang. Okay, going back over here, so this will take some time. On average, usually it's around 1.5 minutes to generate a proof with the proving service. This might take a bit longer, so we're just gonna wait for that. But once this finishes generating, you'll have this, oh, there we go, 83 seconds in this case. We have this download URL that's outputted. If we just open it over here. Okay. You can see that this is our proof with public inputs that we just generated with the service. So going into our next part, I have a pre-recording just to save time. But now that we have generated the proof using the service, we are going to deploy it on a verification contract. So going over here, what we are doing as our first step. Okay, I accidentally restarted the video. Okay, right here. We're changing our directory to the verifier. Let me see if I can zoom in on this, just so you can see this a bit better. Okay, it seems like I can't, so what I can do instead is, if you guys are interested, I can share this demo with you in the slides, so if you want to replicate this on your own, you can just follow these steps. But over here, we're just transferring the contents from our download URL, so that proof with public inputs, into a new JSON file called snark proof with public inputs, and that's under our test data MIPS folder. And then as our next step, going back over here, we're building our benchmark program. And what that does is it converts the proof that was generated by the proving service into the Groth16 snark proof so that we can deploy on the verifier contract. This part does take around 10 minutes, so I will fast forward this a bit. And once you are done compiling that benchmark program, you should have an updated snark proof with public inputs, as well as a verifying key that's generated. As our next step, we are building our caller file, and we're using this to generate a new verification contract on hard hat, so it should output success as a result. And from here, we're going to start running a hard hat node. So that's going to start a new JSON RPC server so that we can do the deployment in the next step. And then in this step, we can also run a hard hat test. So what we're doing is we're seeing if the verifier submits a proof. If so, then it'll pass. If not, it'll fail. And from here, we're deploying our contract on a test network. We're using Sepolia in this case. And we can take that deployed address over here and use it to call our contract. So once you've called your contract, it'll have this hash that's outputted as a result, and you can view the details of that transaction on Etherscan. So that's what we're doing over here, and should output the status as success. So now that we have our proof that was generated by the service, we've also deployed it on our verifier contract. Now let's do an on-chain action with our valid proof. So we are going to mint an ERC20 with our proof. And I have another recording for this as well. If you want to try this on your side, let me reshare this. If you want to try this on your side, what you should do is first clone the use cases repository. And then from there, oh, this is the wrong link. Okay. Not sure why I have the duplicate of this. I will go back over here. So this is the right recording. So what you should do first, clone the use cases repository, and then from there, redeploy your contracts. That's what we're doing in this step over here. And taking your newly deployed address, so what I've highlighted over here, go back to the caller file, and where it says ERC20 token address, replace what's there with your newly deployed one. And you can also go and import your newly deployed address as a new token contract address. And I'm just going to fast forward this a bit. As you can see, we currently have 0 over there because it's a newly deployed address. We haven't minted anything yet, but that will change in a moment. As our next step, we are building our caller file and then using it to mint our ERC20. So you'll have another hash that's outputted as a result. You can view the details on Etherscan. And just fast forwarding this a bit, it should also output the status as success. And going back to our wallet, we can see that we have one ERC20 that was successfully minted. And I just want to mention, if you used an invalid proof, then the execution would revert. It'll say that the proof is invalid. But in this case, since we have our valid proof, we were able to mint the ERC20. And for the applications and use cases, we aren't just limited to on-chain actions like with our ERC20 mint. We encourage developers to try out your own proof of concept applications depending on what you're interested in. If you are interested in using the proving service specifically, We have a limited number of spots available on our whitelist for this initial testing phase. So if you are interested in using it, be sure to go to zkm.io/apply to apply for a spot. And I do want to mention that our DevRel team created a playground where you can do the exact same steps, so importing your Golang programs and using the proving service to generate proofs, but without all of the installation and setup that we just went through. So if you want a tool to play around with generating proofs and then also just see the step-by-step process for this, be sure to head over to playground.zkm.io and you can just play around with it. But here is the QR code for your convenience if you want to apply for the proving service. But other than that, if you guys have any questions, let me know. But yeah, thank you all for listening.